Google DeepMind just published AlphaEvolve. I think a lot of people are going to miss this paper. There's two things that you have to see. So really fast, AlphaEvolve is an AI system that improves code or math or some other thing that we're doing. At its core, it's a large language model, in this case, a Gemini 2.0 Pro, among other ones. But here's the point. They have a few things that's buried here, I think, on page 15. And here's the thing that you need to hear. This deployment also marks a novel instance where Gemini, through the capabilities of AlphaEvolve, optimizes its own training process. So what does that mean? So novel instance means, well, we haven't seen this happen before. This is new. Gemini, so our large language model, our AI, using this AlphaEvolve, so this process that Google DeepMind came up with that we'll cover in just a second, but you can think of it as like our AI model, Gemini, plus some tools that we gave it. That's AlphaEvolve. It optimizes its own training process. So we can read the sentence as like, hey, this is new. We gave our AI some tools and it improved itself. It seems like kind of a big deal. But wait, there's, as they say, more. So you might have heard about the TPU, right? The Tensor Processing Unit. So that's a Google AI chip. It's the hardware on which these AIs are run and trained on, similar to how NVIDIA has the GPU. Google's own technology is the TPU. So designing these chips is a complex and time-consuming process spanning years. It takes months of hard work by highly skilled engineers. It's hard and expensive, and it takes a long time. As you'll see in this video, AlphaEvolve, so again, this is driven by the Gemini LLM, but AlphaEvolve was able to rewrite some of the code, removed some unnecessary bits, and basically kind of improved the hardware stack on which it runs. As they say here, this improvement represents Gemini's first direct contribution to the TPU circuits. And this early exploration shows that this novel, again, this new approach that they've developed here, that they're referring to as LLM-powered code evolution. And this evolution word, as you'll see, is very apt here, right? It assists in hardware design. So you see this picture on this channel many times before. It's the idea of the intelligence explosion. This was proposed by Leopold Aschenbrenner, ex-OpenAI, but he's not the only one. A lot of people are kind of pointing to this as the potential future that's going to unfold over the next few years. And of course, there's tons of debate. Not everybody is subscribed to this idea. Speaking of which, subscribe to this channel. It's the only way we're going to make it through this. Kidding, but it can't hurt. Just subscribe. But the idea is simple. At some point, the AIs will start conducting AI research. They're going to start this, as they say, recursive self-improvement. Right? So the idea that these AIs, they can't walk around the office or make coffee, but they can do machine learning research on a computer. They can work on algorithmic breakthroughs day and night. And in this illustration, in his idea, so he's kind of pointing to 2027 as kind of that inflection point where the AI research becomes automated, where machines, these AI systems, these neural nets are better at doing research than the current sort of human engineers can. Now, again, a lot of people don't believe that it's going to happen, that it's pure science fiction. But as we look at this paper, ask yourself this. So this is 2025. So you are here, right? Let me draw a little arrow. So X marks the spot. That's where we are now. And this is the day that AlphaEvolve is published. The paper is published, and it's also going to be available to some academic researchers. But as you'll see, some of the discoveries or optimizations that this AI model made, Google has already implemented those improvements, and it's been implemented for over a year. Right here it is. AlphaEvolve proposed a very simple improvement, and this solution, it's been in production for over a year. So a year ago, we've already been seeing some things that this AI system has proposed that's been put into production at Google across their vast infrastructure, it seems like. And that thing continuously recovers some percent of Google's worldwide compute resources. So that was a year ago. My question for you is, where are we, let's say, at the end of 2028? Let me know where you think we'll be. Please hit a thumbs up because I think people need to see this, and let's dive in. So Google DeepMind just dropped AlphaEvolve, a Gemini-powered coding agent for designing advanced algorithms. And this thing, while not as flashy as some of the other things that are coming out, can improve certain things we do at a very fundamental level. So this is a new AI agent out of Google DeepMind that evolves algorithms. And evolves, they don't use this word lightly. It truly is an evolutionary coding agent. You can think of this thing as basically having two parts. As I say here, they're combining the creativity of large language models with automated evaluators. This is a little bit similar to the absolute zero reasoner that we covered just a few days ago. In absolute zero, you had two AIs. One is the proposer, kind of like the coach that set up the obstacle course, and the other is the solver. That's the model that's supposed to run through the obstacle course to solve it. Or in this case, they were doing coding problems. Now, AlphaEvolve is not quite the same thing, but it has a similar concept in that we have an army of large language models that provide outputs, and we have evaluators that sort of rank and test those outputs. What's interesting with AlphaEvolve is that we're basically using some of these same models that you and I can use on Google's AI Studio or in the Gemini app. In fact, they're not even the latest models that are out right now. As we'll see in the paper, they're using a combination of Gemini 2.0 Flash and Gemini 2.0 Pro. And these models are paired with the automated evaluators that verify the answers. Now, how big of a deal is this? What were they able to accomplish with this? Well, this process already enhanced the efficiency of Google's data centers chip design, as in the hardware, the design of the chips, as well as the AI training process, and get this, including training the large language models underlying AlphaEvolve itself. So this means while AlphaEvolve is powered in part by Gemini 2.0, it designs a better algorithm to train Gemini 2.0, to train itself. It's kind of improving itself. And it also designed faster matrix multiplication and new solutions to open math problems, showing incredible promise for application across many areas. That's the important part, is that it seems pretty open and versatile and can be applied to a lot of different optimization and computation problems. Here, for example, is the Strassen algorithm. It's used for matrix multiplication, and it was published in 1969. AlphaEvolve apparently improves this algorithm by discovering an algorithm using 48 multiplications to multiply the 4x4 complex valued matrices. The point being is that in over 50 years, no one found an improvement on this algorithm, and AlphaEvolve does. So as you can see here, there's a lot of applications that this thing can improve on. We're already seeing some pretty big things that it optimized. How exactly does it do it? Well, so it combines the Gemini models. Gemini Flash, which is the fast and efficient model, kind of throws out more ideas. Kind of, you can think of it as a brainstorming. While the powerful model, Gemini Pro, provides the critical depth and insight suggestions. Keep in mind they're using a 2.0 Pro. 2.5 Pro is available to the general public right now, and we're even expecting something bigger to drop very, very soon. 2.5 Ultra, perhaps? So currently it seems like there's still a lot of work to do for the human scientist and engineer. AlphaEvolve does handle a lot of it, but there's still some sort of setup that's needed. So we can see here in green, that's the scientist or engineer. They provide the stuff in green. Everything in blue is the AlphaEvolve. So the scientists provide the what. AlphaEvolve handles the how. We have a prompt sampler, the ensemble of LLMs. So in this case, Gemini Flash and Pro. We have the various evaluator pools and automated evaluation code. We'll get to that in just a second because how they did it is actually quite interesting. We're also given the program database. So this is the thing that we're trying to improve on. So conceptually, an easy way to kind of think about it is, say you're trying to load a pickup truck or a U-Haul of some sort, and you have some boxes and furniture that you have to fit in there, and you're trying to save as much space as possible to load up as many boxes as possible. So you probably have some existing sort of a program in your mind that you're going to execute, right? So put the first box in the back left of the truck and then keep adding boxes or whatever, right? We all have some approach. We've all played at Tetris. We've probably all moved and had to engage in this exercise of trying to stuff as many boxes into a car or a truck, etc. So very simply, what AlphaEvolve would do here is just to come up with a lot of different approaches to pack those boxes. It would sort of evaluate those approaches, and the final sort of evaluation code would see if the new approach would save more room than the approach that you were doing. And at the end, you sort of emerge with the best program. So it's pretty simple, but the complexity lies in that evolutionary process that they've designed. So the evaluation function basically allows for the best versions, the best proposals to survive and get improved. So if the LLM proposes a promising solution, we see that reflected in the evaluation and we try to create more similar solutions. So this is from the paper. So this is how they do evaluation to track AlphaEvolve's progress and to select which ideas to propagate in future generations. Each new solution proposed by the LLMs is automatically evaluated. So again, if let's say there's three solutions that are proposed, they get graded, right? Let's say this one emerges as sort of the best one. It has the highest score. These two are not so good out of the gate. This is the one that will sort of get to propagate and continue its evolution. And from here, we might find other ones that work, and each one gets graded and automatically evaluated. How they approach this is they have a couple different ideas to make this process faster and more efficient. One is the evaluation cascade. So as they're testing these various approaches, these ideas, these hypotheses, they will in general start with the easier tests. So they might start with test cases of increasing difficulties. So these new solutions are evaluated quickly on the easy stuff and then progressively more and more difficult tests. And this allows to prune out the less promising solutions quickly. Also, the LLM models themselves generate feedback. So for example, some desirable solutions have certain characteristics that are difficult to capture precisely in the user-provided evaluation function. For example, the simplicity of the newly discovered program. And these properties can be graded using separate LLM calls and added to the dictionary of scores to steer evolution. So while some criteria can be reduced down to a number, like how fast is it on a scale of 1 to 10 or something like that, or in the case of our matrices multiplication, how many steps does it take? Some other things are harder to just quantify like this. This is where the LLMs can come in and sort of describe certain solutions or characteristics. They can add some notes that can be used to continue kind of grading how good that solution is. And these evaluation functions can run in parallel. Of course, if we run these individual evaluations one at a time, this would really slow down the rate at which the new generations would appear. As far as the evolution goes, one thing they note here is that a key challenge is designing these things in such a way that exploration and exploitation is balanced. Exploration is where we're just trying stuff out to see what works, what doesn't work. We're not necessarily focused on, let's say, winning. Exploitation is more once we found something that works, we kind of try using that to kind of rack up the points, if you will. This is a similar approach that we use with reinforcement learning. Interestingly, if you think about how humans work, we tend to be more about exploration in our younger years and more about, we probably wouldn't use this word exploitation, but we tend to kind of figure out what works and we stick with it as we get older. We're more open to ideas and trying new stuff when we're younger. And this was the process that they've used to optimize the computing ecosystem, Google's actual computing ecosystem, including data centers, hardware, software. If you think about the broad range of things, these little savings and efficiency improvements, how much they're going to get multiplied across the entirety of what Google is, this could be easily in the millions of dollars saved. As the little foundational improvements, they really tend to compound across the entire infrastructure. Google has a system to kind of orchestrate their vast data centers. They've called it Borg, of course. What else? I'm sure some people at Google probably try to resist naming it that, but as you might have already guessed, resistance is futile. And the solution, now in production for over a year, continuously recovers on average 0.7% of Google's worldwide compute resources. Another win for AlphaEvolve was improving a already highly optimized arithmetic circuit for matrix multiplication. And this proposal was already integrated in the TPU, the Tensor Processing Unit, which is Google's own chips, their AI accelerator. So kind of how NVIDIA has the GPU. Google's very own sort of version of that it's a little bit different, but it's called the TPU. And here's AI enhancing its own sort of AI's training and inference. So between this and the hardware design, as you can see here, it's almost kind of doing its own self-improvement across both the hardware and the software. So here, by finding smarter ways to divide large matrix multiplication operations into more manageable subproblems, it sped up a vital portion in the Gemini's architecture by 23%, which leads to a 1% reduction in Gemini's training time. Now, the amount of resources that can go into training these AI models is massive, or can be massive for some of the bigger ones. And with scaling laws, we expect that to increase. So while 1% may not sound like a lot, it's going to translate into massive savings in both capital for Google, but also in terms of energy, time, etc. An interesting point in the paper is the idea that things like AlphaEvolve free up humans to do higher level tasks. So here's where they mention the 1% reduction in the overall training time. But in addition, the use of AlphaEvolve significantly reduced the kernel optimization time from several months of dedicated engineering effort to just days of automated experimentation. So from several months of humans, completely focused on doing this thing to days of automated, right? This computer program running, this AI kind of taking care of it. And this speeds up the deployment, but also it allows the engineers to dedicate their expertise to more strategic, higher level optimization problems. And this little line, I think, here is very important. This deployment also marks a novel instance. It's new, never before seen. We're seeing a new thing happen here. That thing is Gemini, our AI chatbot, the large language model, through the capabilities of AlphaEvolve. So keep in mind that AlphaEvolve is Gemini plus some other things, right? So Gemini, through AlphaEvolve, optimizes its own training process. So Google here again is saying this is something new. We're seeing this AI improve itself, or at least its own training process, so that with these new training processes, we can create better versions of it. So whether you're calling that self-improvement or self-evolution, this is obviously incredibly exciting. And of course, Gemini not only improves its sort of software, its own training process, it also contributed to improving the TPU, the tensor processing unit, the chip that it's trained on. So, I mean, we're seeing it's improved both the software and the hardware stack on which it's built. So this is that idea that we've been kind of talking about on this channel for quite some time, the fact that humans, we build kind of a version 1.0 of the AI. That version 1.0 will build kind of the version 2.0. It will build its own sort of descendants. Now, obviously, I'm not saying that this is happening 100% quite yet, but we are beginning to see these things happen. And Google DeepMind is pointing it out here, right? The first direct contribution. So this is Gemini's first direct contribution to improving its hardware, a novel instance where it improves its own training process. And of course, Google famously kicked off this whole LLM race by publishing a paper called Attention is All You Need, introducing the transformer architecture. This is used in the majority of modern neural networks, ranging from LLMs to AlphaFold. Again, so this is what kicked off a lot of it. It's a scalable architecture that we use now to build these AIs. The core computation of transformers is the attention mechanism. Attention is all you need, as they say. And here they kind of walk you through how that sort of what that gets built on, kind of the components, but basically they're challenging AlphaFold to optimize sort of one of the components of this architecture. And the task they gave AlphaEvolve is a particularly challenging task because of two things. One, it's designed for debugging purposes rather than for direct editing. And two, it's compiler generated and already highly optimized. So every solution proposed by AlphaEvolve was checked against the unmodified code. It was rigorously confirmed by human experts to be correct for all possible inputs. So basically here they're saying it wasn't hallucinating this, like it was for real, if you will. And the thing that AlphaEvolve was able to do is to provide meaningful optimizations. One part that they were looking at was sped up by 32%, and another part was sped up by 15%. The results demonstrate the ability of AlphaEvolve to optimize compiler-generated code offering the potential of incorporating discovered optimizations into existing compilers for specific use cases, or in the longer term, incorporating AlphaEvolve into the compiler workflow itself. So what's the big deal about that last part? Basically, what it means is that this thing can crack a lot of fields and areas that we think of as mature, like where we've had a lot of time to figure out how to do things right, how to optimize it, where maybe we're thinking, okay, this is as good as it gets, as efficient as it gets, and here comes AlphaEvolve. And it seems like it's going to be able to introduce massive improvements and optimizations across the board in a lot of very fundamental areas. Right here, they're saying we believe AlphaEvolve could be transformative across many more areas, such as material science, drug discovery, sustainability, and wider technological and business applications. It's everything. Basically, as far as I can tell, anywhere where you can kind of quantify the outcome. So anywhere where you can give the automated evaluators some sort of a metric or something that they can verify, something that they can grade. It seems like this would work for that area. If it's a little bit more subjective, then maybe this won't apply, but anywhere where we can kind of quantify the outcome that we're looking for, and for a lot of optimization things, that's how it is. Right. So for our loading the U-Haul problem, right, if you're able to save space, there's a specific formula for that, right? So if I put in my boxes and it took up, X amount of space, and this thing can figure out how to take up 5% less space, then it wins at optimizing that problem. So if I can quantify it, it can probably take a crack at it, and it seems like it might be able to find optimizations in fields that we've considered to be mature and mostly optimized, which is kind of exciting. But even if we zoom out in the greater scheme of things, what's interesting here is notice again, the researchers are saying that Gemini, with this scaffolding, right, with the attachment of everything else that AlphaEvolve is, right, because again, the LLMs ensemble, right, so this is the collections of the LLMs that they're using, some that are faster, cheaper, and some that, are a little bit more expensive to run, but, are able to provide better, deeper research, better outputs, etc. Right. So our AIs, our LLMs kind of go in here, and the rest of it is kind of the stuff that's coded up around it. Right. So this is the system that kind of makes everything work. But I think it might be reasonable to think that, if we put a good model in here, this entire system works better. What happens if the model that we put in here is able to improve the next generation of models, which again, we're seeing in this paper that it's doing, and it's able to improve not only the software, the training, but perhaps even the architecture of the neural nets, and also the hardware, the chips that we're training them on. And some of those things contribute to an improvement of the next generation of models. And then we take that generation of models, the new and improved, if you will, and we put it into the system. Again, does that improve the system as a whole, contributing to creating an even better hardware stack and software stack and architecture? This is kind of what we think of as the beginning of the intelligence explosion. So basically the idea is that these AIs, they don't have to automate everything. Really, if they just automate AI research, meaning improving how well AI is able to do stuff, well, that would be kind of a big deal, because then it would be recursive self-improvement. And some people are saying that this would be kind of the start of that intelligence explosion, as better and better models are able to provide a better and better sort of next generation of models. And we kind of see this exponential explosion in intelligence. But let me know what you think. Leave me a comment. Am I hyping things out of control? Again, keep in mind, this is just the very, very beginning. We're beginning, as the researchers of the paper put it. They said, this is the first example of it doing this. This is a novel example of it doing this. So we're beginning to see examples of this, and assuming that this process continues, it's probably going to speed up. But let me know what you think. Do you believe that this is an example, however small, of an AI improving itself, both its software and its hardware? Let me know if you made it this far. Thank you so much for watching. My name is Wes Roth, and I'll see you next time.